things. So, yesterday I showed you a little bit of teaser on the Euler. So today I'm just going to show you the cool physics that we have been discovering. So I will just go deeper into how this non-abelian braiding, how this works, and then how we are doing it, and then especially what new kind of phases that we have discovered for this multi-gap non-abelian topology Euler class under periodic driving. So that is kind of the blockade part of the new physics and topologies that I will talk about. But then I will go to the quench dynamics. So as another out of equilibrium setting. So in recent years, in quantum simulation experiments, so this technique, quantum quenching technique, suddenly changing the Hamiltonian between topologically different, distinct phases, have been established as a really powerful tool. So it allows us to discover Neve invariants and Neve connections. For that, I need quaternions. So there I go into the pedagogical mode and then show you what quaternions are, how it works, how we are employing it on out of equilibrium quench dynamics. And as yet another signature of Euler class, so you can just look at this quench dynamics of it. But because Euler class is too complicated, maybe, let's look at the churn case first under quench dynamics, then go to Euler class. And as a bonus, I will show you anomalous blockade topology. So this is the Euler class. So under C2T or PT symmetry, we can have this braiding of band singularities in the momentum space. So I need this C2T or PT symmetry to restrict the reality condition on the Hamiltonian, and I don't need them from there on. So this is not a symmetry indicated topology. It cannot be captured by those K-theory equivalent descriptions. And so this has been being developed for the last couple of years. The invariant is given by this non-abelian Berry curvature. So a nice way of understanding, seeing this, how does braiding, non-abelian braiding works, is through Dirac strings. So I will also show you the math, but it is, in view of time, it's much easier to follow how Dirac strings works. So what I'm doing here, imagine that I start from a 3-band system, completely trivial, nothing is happening. And I'm going to induce band inversions in gap 1, between 1 and 2. I will label them with triangles. Empty field means that they have opposite charges when I just create them. The ones in gap 2 will be filled and empty circles, okay? So now I start from, this is the Brillouin zone. I look from the top, all 3 bands, completely trivial. I can induce some band inversion in gap 1 and separate 2 Dirac cones, okay? So these will be the empty field circles. They will be connected by a Dirac string. So this Dirac string is, whenever I have a Dirac cone, I stay within one eigenstate and I try to do an adiabatic transport around, imagine graphene, okay? I have 2 Dirac cones and then I just follow the first eigenstate. I can keep fixing the gauge of this eigenstate around the Dirac cone, okay? Until some point, it has to flip its sign. So this Dirac string is where the sign of the wave function is flipping around the Dirac, because the Dirac cone has pi phase, it has to flip. There must be a discontinuity in the phase of the eigenstate. So it is a gauge object. 2 Dirac cones are connected by it. And in the gap 2, I create 2 more topological charges like Dirac cones. I'll separate them plus and minus 1. So if I have C2T or PT, if I have Euler description, what I can do is that I can take this Dirac cone in gap 2 and then move it in the Brillouin zone. So imagine that you're changing your Hamiltonian. Okay, so my collaborators have been doing this even with strain, for example. Okay, so you just want to locally change your Hamiltonian. So if I take this Dirac cone and then cross the Dirac string in the other gap, in the adjacent gap, its charge flips. If I take this one and then cross the Dirac string of the other gap, it charge flips. So now they both have positive charges in gap 1 and negative. So I can play this game one more time. I create one more pair in gap 1. I take this Dirac cone and then cross the Dirac string, it becomes filled. And then I take this one, cross the Dirac string in the adjacent gap, it becomes positive again. So now these Dirac cones in gap 2 again have opposite charges. And if I clash them head on, they can annihilate each other in the same way that I created them. Here, they could not. They have same charges. Here they can. So if I just clash them head-on, I annihilate them, and I end up with this space. There are 4 Dirac cones in gap 1, nothing in gap 2. So now it looks like that I did some trick, because I cannot create topological charges out of nowhere. That's why I was creating them in pairs, right? You cannot just like create charge out of nowhere. But now here, I have some Dirac cones, they all have positive charges, and I don't have their negative counterparts. So it looks like that I did some trick, but I didn't actually, because this phase is something that I can come to only through via braiding with the third band. So this is why this is a multi-gap topology. So this is why it's entirely different what's being known in the single gap topology, and I need braiding between it. So, and this gap is complete, this band is completely trivial because Hamiltonian is real. It doesn't have any Berry curvature, no Chern number, nothing. Okay, so I am allowed to do this in Euler class because if I have C2T or PT symmetry, so if I have C2, C2 takes K to minus K. Time reversal symmetry takes this back, but also complex conjugates. So if I have C2T symmetry, Hamiltonian must commute with its complex conjugate, means that it must be real. And if I have a real Hamiltonian, so this is a 3 by 3 Hamiltonian, its eigenstates, 3 by 1 vectors, they can be also found real. And these are eigenstates, they are already orthonormal, and I can treat them as vectors in SO3. Forming a dry band, okay, because they form a frame. So, and the charges in this frame, pi1, SO3 of DO2, I need D2 because when I form my frame as like, I can write this third eigenstate as the cross product of the other two, I need to fix a sign here. Okay, this could be, I could also define the frame in the other way with the minus sign. So pi1 charges of this SO3 or D2 take values from the quaternion charges, which is an abelian group. It means that when I have a Dirac singularity in this dry band, and then if I just like twist this, like take these Dirac nodes between psi 1 and psi 2 and then 2 and 3, after one rotation, they don't come back to itself. This is exactly how like Dirac belt trick works, right? So if you just like twist 2 pi, it doesn't come back to itself. You need to twist twice to come back to itself. So that's why they have non-abelian pi charges. Okay. So while we are doing these Euler non-abelian braiding, this is the math that we are following. But I can also just like, I mean, I will be just like showing you also some calculations based on this, but we can also, we might as well also follow the Dirac string picture. And if I am in this nice orientable phase that like the third band is completely gapped, this non-abelian Euler curvature can be also expressed in a similar form, close to Pontryagin formula that you might remember from the Chern number. But now they have this can only be even here, twice the value. I will come back to this slide back when I show you how we use this description to identify the quench signatures of the Euler class, okay? So now this is how the braiding works. By the way, if you have any questions, please interrupt me. So this is how Euler class works. Yes.
Is there an easy way to understand why that first step in the braiding happens? Why does something from bands 2 to 3 crossing the line between something from bands 1 to 2 have to mean the charge changes?
So it's exactly because of this map. So I have the frame, and then when I have a pi1 charge there, this one, so these empty, like these triangles actually quaternion charges plus minus I, and then circles are plus minus j. If I had another one, I will also show you plus minus k. And then when I take down one, like around each other, it corresponds to like this is spin. If you just like rotate it by 2 pi on SO3, you don't come back to yourself, right? So it's exactly the same thing. So when you have this dry band, and then you have a singularity around it, and then you have another singularity in the other gap. When you take them around, this frame doesn't come back to itself. You need to do it twice. So that's why crossing a Dirac string flips their charges. Yeah. Any more questions? So for this Euler class, so now adjacent gaps are important, right? I'm braiding through the adjacent gaps. So now one interesting question is that if I have floquet, I have 3 bands. If there's periodic driving in this system, I'm going to have infinite many replicas of this. So I have this anomalous gap, which can be, they take this role of an adjacent gap. What happens if I have, or this multi-gap topology, if I have a periodic driving? And then the answer to this question turned out to be really interesting, that there are new phases that come through braiding through this anomalous gap. And then we can do this braiding in a Floquet-induced way. So, so to put things into context, so let me just consider a Kagome lattice. Okay, so this is a 3-band model, minimum, it's good. So I just consider some sublattice offsets, but even in the sublattice offsets, this Kagome lattice is already interesting. It has a flat band. Flat bands are interesting. We also saw yesterday. And this is the Dirac string configuration in the Brillouin zone. And interesting, because Kagome lattice, undriven Kagome lattice, already has C2T symmetry. So it's already real. And it already has an Euler description. And this gamma node here has an Euler charge, 1, saying that there are actually 2 nodes here that they didn't analyze each other. So I have the KK prime nodes in the Brillouin zone. They must be connected by a Dirac string. So these KK prime nodes, if I just calculate this non-abelian Berry curvature that I showed you in the first slide, it integrates to 0, which means that they have opposite charges. And then the Dirac string is there as a gauge object. Okay? So now I take this Dirac string and I want to apply some periodic driving to it. So normally from our instincts from the Chern insulators, we want to break the time reversal symmetry, right? Here, I don't want to break time reversal symmetry. I mean, time reversal symmetry in its own is not important. You need to protect C2T symmetry. So it's some additional symmetry. If you can just protect it, that's all good. But here, this is just spinless Kagome. So I want to apply some drive. So I cannot apply some circularly polarized light. I cannot shake circularly. That breaks time reversal symmetry. So what I can do is linear shaking, linearly polarized light, or in the spirit of these stepwise drives, I can also do some back and forth driving that doesn't break time reversal symmetry. So if I apply this linear shaking, linearly polarized light, so this vector connection goes and couples to the momentum under minimal coupling, okay? And so now I have some tuning parameters that I can play in my Hamiltonian to induce these braiding. So I have the frequency of the drive, amplitude of the drive, and so without loss of generality, I will consider shakings along x direction only. So AX, frequency, omega, and 2 sublattice offsets. The third one, I just set it to gauge the rate, so to center the bands, okay? So 4 parameters, I will play with these, and then I want to show you what kind of cool things that we can do. Okay, so, so one thing that we can do is that starting from this Kagome undriven system, the moment that I start shaking, this linear shaking breaks C6 symmetry. And then that C6 symmetry is the thing that protects these gamma nodes. So the moment I start shaking, this gamma node separates into 2, okay? They are connected by a Dirac string, and then they still have the Euler charge 1. So now I want to apply some sublattice offsets, okay? Just play with the sublattice offsets to just change my Hamiltonian. So if I decrease the A and C sublattice offsets, so these gamma nodes separates further. KK prime come closer. And then if this gamma node crosses the Dirac string in the other gap, it flips its charge. And then if I keep decreasing, so now the Floquet in this anomalous gap between the replicas of the bands, they touch, and then I have a band touching, and then these new green square empty field nodes are created in the anomalous gap. They cross 2 Dirac strings, so they still have opposite charges. They flip their charge twice. And then already this gamma node annihilates itself with its pair across the Brillouin zone, leaving their Dirac string behind, okay? So now if I keep doing it, it looks like that KK prime are gonna annihilate each other, but these anomalous nodes behave faster, so this turns into a little bit of race, and they go annihilate each other right in the middle of the KK prime nodes, leaving their Dirac string behind. Now KK prime can never annihilate each other within this patch because they need to cross a Dirac string and then they have same charge. If I calculate the Euler class, I indeed find 1. So this is Floquet-induced braiding. And this is an anomalous phase that I can come through only in Floquet system because of the presence of this Dirac string that KK prime cannot annihilate each other, okay? So another example, anomalous Dirac string phase. So instead of just like playing with the two sublattice offset, if I just like play with only one of them, gamma node again separates. I create the anomalous nodes here, but now KK prime already annihilated each other, gapping, and then they left their Dirac string behind. So gamma nodes cross one Dirac string, KK prime, and then they flip their charges. They annihilate each other. They leave their Dirac string behind. And then for these nodes, they go to the third possible endpoint. I mean, they can only annihilate each other with their pairs in the symmetric points, right? And then they leave their Dirac string behind. So now I have this gapped phase. It looks boring. Nothing is happening. But it's nothing but boring, because this is a phase that, like, I have 3-band system, and then I have Dirac strings in all possible gaps. This gap is also possible in flow K. I have an anomalous Dirac string, and this is the maximum configuration of a Dirac string that you can have in a 3-band system. And because these strings, so if there is a Dirac string, it means that there is a pi Zach phase, or difference of pi Zach phase with the atomic limit. So if I take this anomalous Dirac string, and then if I put it in a finite system in some ribbon geometry, because I have this Dirac string here, it shows as an anomalous edge state lying there. And if you just like look at it, it's just like completely localized at the edges as it should be. So this is exactly like that, because I have a pi phase here, this pi phase gets projected on the edge state. So more Dirac string configuration. So for your experts, so you know, in flow K, the moment that you start shaking, if you keep increasing the amplitude of your shaking, you can invert the spectrum, because the tunneling amplitude gets normalized with a Bessel function, and you can hit a Bessel 0 or dynamically invert the bands. So if I start with the flat band being at the top, I can invert that one to be at the bottom. And then, but this actually tells us that this dynamical inversion in Kagome has to go through non-abelian braiding with rearrangement of nodes. In the original gamma nodes, the circles arrange themselves as in a like C6-like symmetry, just like as if they were KK prime nodes, and then KK prime became like take on the role of a gamma node. So this is the anomalous Euler. Okay, so this is one signature of anomalous Euler that I show you. So now I want to show you another signature of it in quench dynamics. So do you have any questions? Yes. In what way?
So when you mentioned that the band dispersion gets renormalized by Bessel functions,
yes.
So that basically means that you are shaking at frequencies that do not hybridize the bands, right?
Yes.
So that's an
exactly. So this is, I'm just like, so you mean here?
Yes.
I'm just interested in the dynamic inversion.
Right.
Yeah.
Can there be some interesting things that arise if you try to hybridize the bands in any way?
Could be. Yes. I mean, in principle, those are the things that I was trying to do, because these anomalous nodes are really interesting. And then, as I showed you yesterday, I mean, they can be measured in experiment, as done in Munich. So those are interesting. But to be honest, I haven't done it in this case. But you would induce also band inversions there, and then things becomes really indeed more interesting in that case. Okay. Yes.
Well, about the Dirac string, like how arbitrary are they? So the endpoints are fixed, but is there any possibility of moving experimentally?
Yes.
Like, are they theorists just in your head, or you see a defect in the wave function? Yeah. So, could we image them somehow or anything like that?
This is a Dirac. This is a direct manifestation of a Dirac string. So as you said, so they are gauge objects. So that's why sometimes I draw them wiggly, and then sometimes I draw them straight lines. So they are gauge objects. What you know is that, so you have the two lattice vectors of the, so you have the B1, B2 lattice vectors. So what you can calculate is the Zach phase along B1 direction, for example. And if this gives a pi phase jump, then you just like integrate along B1, for example, it tells you that you cross a Dirac string.
So it's like going across a dark soliton. I mean, does the wave function have to vanish on the? Can I think
no.
of it as a vortex?
No, wave function
or
has to change.
just
its
change
sign.
by pi?
Exactly. Wave function should just like at that point pick up a minus sign. Exactly.
But it can't change instantly, right? I mean, you're saying the amplitude doesn't change. I mean, it needs to be.
Exactly. It just picks up a minus sign. So
There's no node of the wave function as you go through that.
no.
Hmm.
No, and these things are just like when they're just like lying around here, so they are not at a fixed point. So they can be anywhere. It could be already at the edge of the Brillouin zone, somewhere in between. You just know that when you integrate it along one periodic direction of the lattice, if the wave function picks up a sign, you cross the Dirac string. So it's just like there's a pi, there must be a pi strip. So it could be at the edge of the Brillouin zone. So that's why I have the gauge degrees of freedom of choosing that. But it's really just the sign is picking up a phase. Sign is changing. Okay. So now, if there are no more questions, so let me tell you a little bit of quaternions. Okay, so quaternions are fun. So this involves hope maps. So I showed you the Chern number yesterday. I have this pi2 of S2. That's if I have a Bloch sphere, if I wrap it, I have the Chern number. That's nice. So now hope map is a map from S3 to S2. Okay, so locally, you can imagine this thing that I have some S2, and on every point on it, I'm attaching some S1. So if this was a trivial map, these things, they don't link. So, okay, so this third dimension that you are putting there, there's nothing interesting happening. But if there is a non-trivial map, these two links that S1 circles that you're attaching on your circle. So by the way, this is a way that like we can just visualize it. Okay, I'm trying to, so don't hold me with mathematical precision. So if these links here, if there is a non-trivial hope map, they must link here when you take the inverse image of. So this is the color coding. So when you take any point on the Bloch sphere, if you go back to S3, try to visualize it, then they would be linking or not. So you can imagine this thing as some kind of Hamiltonian that has 3 parameters, but mapping to a 2-dimensional Hilbert space. And this is indeed something called, there's something called Hope insulator. They have been also gaining a lot of attention, and this has been actually originally proposed by Joel. So it's a 3-dimensional insulator that falls entirely outside of K-theory. They have pretty interesting properties, and then even like some proposals, but also some 3-dimensional realizations very, very recently. So I will not go to this 3-dimensional parameter space in a 3-dimensional crystal way. I want to do it in a time-dependent way. Okay, so that's why I'm going to do quaternions, so to explain you what this whole hope map is. So quaternions extend Chern numbers to C2. So they live in R4. So I want to just like, so I like this quote from John Baez that I come across to with through Mehmet Oktar. So he says that there are exactly 4 non-division algebras. So the real numbers are the dependable breadwinner of the family, the complete ordered field we all rely on. You would all agree, I believe. Chern numbers are the complex numbers are the slightly flashier but still respectable younger brother, not ordered but algebraically complete. Quaternions, being non-commutative, are the eccentric cousin who's shunned at important family gatherings that I will show you today. And octonions are the crazy old uncle nobody lets out of the attic. They are non-associative. They're also useful in string theory. We're not going to go there. So let's look at quaternions now. Okay. So I want to extend Chern number. Why do I say complex numbers C to C2? Okay. So a quaternion, when I have just a real number, if I want to make it complex, what I do is just x0 real part, x1 times I, right? So this is like R2. So now quaternions have 3 imaginary components, I, J, K, and then 1 real part, so living in R4, okay? So this I, J, K are all imaginary units. So they all square to -1. And then they have this right-hand rule. So they are, just like their cross product gives the other one, okay? So I need some definitions. A versor is a quaternion with a unit norm. So I can define it as some real part plus some vector. of this three-dimensional vector, but imagine that. So this is a vector, but vector in this complex basis, okay? And I can also, if this is normalized, I can also write it as some cosine sine with some normalized vector there. And now there's also a pure quaternion. It's a vector with no real parts, so it's just the vectors, imaginary parts, okay? So with this versor, because they are normalized, they must, in R4, they must span S3, and a pure quaternion is an element of R3, okay? It just has 3 elements. So now, if I take a vector, pure quaternion, and act it with a versor like this, so this is the inverse of a versor, so it's normalized, I get another vector. And I preserve the norm because inverse of the versor includes the norm in the denominator, okay? So this norm preserving action that I call R of mu generates rotations in 3D. This is another way of just like writing our normal SO3 rotations. So I have a vector T, and then I am rotating it around the versor vector V by an angle theta, okay? So I can write this action R nu of T equals T prime. If I just like insert these versors here, I can just like find it. If I just like take for T, for example, if I take the unit vectors, I can just like find its elements like column by column, and can I just like form this matrix. And then if I just like compare this thing with the traditional rotation matrix that we know from 3D, you can actually see that this is indeed the rotation around this axis that we are giving by the angle given by the real part, okay? So these are the rotations. Quaternions defines rotations in 3D. How does this define the Hopf map? Because I promised you a Hopf map. So now a versor lives in S3 already because it's normalized, right? And for this pure quaternion, it's a vector. If I take it to be a unit vector, this lives on S2 in this R3, okay? Which means that this rotation matrix that I wrote here is a map from the versor space S3 to S2. So each column of it, when I act this on some T, like some vector, defines a Hopf map. So this is another way of seeing how Hopf map works, because it's a map from S3 space to S2 space. And then I can calculate the Hopf invariant by in terms of these quaternion values, okay? So this is the Hopf map. It's pretty mathematical, it's cool, but this is actually something really observable in the experiments that we can implement this. How does it work? So now let me apply this quaternions, Hopf maps in the context of quench dynamics. So what I imagine that I have some two-dimensional system, and then I imagine Chern class. Okay, so if I start with some completely trivial initial state, okay, it's 0, 1 everywhere in the momentum, and then I want to suddenly change the Hamiltonian to some other Hamiltonian. Okay, so now this state as each k, depending on what this value is, it's going to evolve. Okay, just on some normal unit system. And then when this reaches the 2 pi, this evolution, so time evolution is periodic. It is a circle, S1, right? So what I mean is that if this Hamiltonian has some 2 bands, but I might, for topological purposes, I can just flatten it, and then I can just like normalize its length. So it's going to be exactly periodic at 2 pi at each k momentum point. So this time evolution forms a circle. It will come back to itself. You can imagine it's precessing around the Bloch sphere, but it has to come back to itself. So that's one S1 circle that we have. So the momentum space, if I take this thing to be the two-dimensional thing, so momentum space is 2 torus. I have one S1 circle. So this makes the time is also periodic. This makes a 3 torus, which I can map on 3 sphere. And then the Hilbert space that I consider is a two-dimensional Hilbert space. At each point, the wave function state lives on the Bloch sphere. So it means that this time evolution that I write here defines a Hopf map from the parameter space S3, kx, ky, t on the Bloch sphere. So if this Hamiltonian is trivial, So you can imagine that at each k point, this Hamiltonian points to this direction. Okay, it's completely trivial. And then at each k point, my initial state points here. And then the moment that I quench, this state will evolve around the process around the Hamiltonian. And this will be a trivial thing because pi1 of these S2 circles are trivial. So everything is, I'm not wrapping the sphere dynamically because that's what non-trivial Hope map was dictating. But if this Hamiltonian is non-trivial, so it means that this Hamiltonian has Chern number 1. It has 2 states and then they Chern number 1 and -1. This Hamiltonian vector wraps the sphere. Okay. So, and then at each k point, I start from here. So for the k points that like that lie, because Hamiltonian wraps everywhere, right? Some of the k points Hamiltonian will lie around this axis. So this initial wave function is not going to rotate, but for other points, it will rotate. And it will dynamically cover this S2 sphere, inducing this non-trivial Hope map coming through this thing. And then if I have a non-trivial Hope map, if I take 2 points on S2 and then take the inverse image of it in my parameter space, what does it mean? I just like decide, so let's say that this is the blue point on S2, and then I just like write my kx, ky, t parameter space. And then whenever, so wave function is rotating at each k point somewhere. So whenever something points to this direction that I choose, I put a dot at that kx, ky, t, okay? And if I trace them, they will form circles, this inverse image, okay? And then if I take 2 points, blue and orange on the block sphere, they will link because of the non-trivial topology of that Hamiltonian. So this is what's called a linking number, okay? That is the topology is protected by the topology of knots. So mathematically, we can do this. I can just like write this time evolution in the usual Rodriguez formula, right? And then this will look like in terms of quaternions, it will look like x, the real part and then some imaginary parts like this. This is something you can see because you know that this rotation can be also, this unitary evolution can be also expressed as rotation. So you know its term, you just need to write it down. And then with this comparison that I showed you, you can actually identify these real and imaginary components of this time evolution. And then if you know these real and imaginary components, because you know that this is a rotation, you can actually insert these quaternion components in the Hope formula. So now Hope formula is a 3-dimensional invariant, right? I have an integral on, because this is in S3. Okay, so this is an integral in d squared k and dt, and then these things have time dependence here. But if you actually insert it, this time integral can be easily taken out, and you will see that Hope invariant really reduces the Chern number dictated by the Hamiltonian. Okay, so now this looks like really fancy math, but this has been observed in experiment as the first observation of a linking number. So what Christoph and Klaus did in Hamburg was that you can start with some optical lattice, some 2-band system, you're in a really deep lattice limit, everything is sitting in one sublattice, okay? And we want to probe non-trivial topology, right? Non-trivial Chern number. What you can do is then, for example, send circularly polarized, right? Or suddenly start shaking. So from this trivial state, you can suddenly change your Hamiltonian, suddenly change your laser, and then the Hamiltonian, this state will evolve on the block sphere under this non-trivial Hamiltonian. And then to do the experiments in cold atom experiments, you also need tomography, which means that you need to quench it back, which was something that we had to work out. But long story short, so while this state is evolving under this non-trivial Hamiltonian, you can do a tomography to this state. So you have the block sphere, and then they can look at this block sphere from the top. Okay, so state is evolving. So this is at some time index, this is how the azimuthal angle profile looks like. So you can detect the vortices. So whenever the state protects around North Pole or South Pole, this will look like a vortex in the azimuthal phase profile. And then here they are marked. And they will change, right? Some states will just like reach the North Pole at other times. So they track this thing for all time indices. So when I just like look at the just like sum of over all time indices, when the Chern number is 1, you see that there is a vertex like this, some line that like this linking number pre-image that I showed you. And then there is another one that's just like linking. So things are linking because time, so I have the kx, ay, and t-axis. I don't know why I draw it like this. So this time is also a circle, okay, 2 pi, and then I'm integrating along all t, and then there is a vertex present at all times t, but because time is also a circle, so this will close back to itself, so it links, tells you that Chern number is 1. And when it's not linking, Chern number is 0. And then indeed, when we do this thing for a larger range of parameters where the Chern number is 0 and then Chern number is 1, and then you keep quenching to these data points, and then whenever Chern number is 1, it links, it doesn't link. There are some circles, but they don't link. So this is really a way of measuring the topology by like counting the holes on a donut or a pretzel, okay? So you're just like, links or not links. So this is the Chern number. So now how does it work for the Euler class? So I showed you this thing that like Euler class can be represented. These eigenstates are real. I can always represent it as a dry band on a vector space, right? And if I am in this special case when this N3 vector is completely, the third eigenstate is completely gapped, I can write this thing as a cross product of the other two always, but then I can express this Euler invariant, something like a Chern number formula, okay, like a Pontryagin formula, but it will be even. So if I am in this case where the third gap is completely, third band is completely gapped, I can always imagine this thing, something. So something is happening between the eigenstates 1 and 2. Okay, so I have the non-trivial nodes there. And this third eigenstate is, as I said, so completely trivial because its eigenstates are real. It cannot have any Berry curvature. It cannot have any Chern number. So this N3 is, although itself is completely trivial, the other two eigenstates have something interesting in between them. And this something interesting in between them is encoded onto N3 because it is always the cross product. So it is tracing. And then it means that for this Euler number to be non-trivial, it has to wrap the sphere itself, okay? So this gives me motivation to express this dynamics on the S2 sphere always. So now imagine this thing, what happens if I quench with a non-trivial Euler Hamiltonian? Because signatures, experimentally observable signatures of Euler class, although they are really interesting, they are tricky to get, okay? So now imagine that I start with some completely trivial state, 1, 0, 0 everywhere. And of course, because on this block sphere that I showed you, this just points along one of the eigenstates, okay? So this lives on S2, it's good. And if I quench it, so momentum space is a 2 torus, time is a circle, so this again forms a C3, which I can map to S2. So there's some potential to write a Hopf map here, okay? To observe this non-trivial Euler one. But what is going wrong is that when I start evolving this wave function, although it was completely real at initial time, it's going to become complex. And if it is complex, I cannot express it on an S2 sphere. It has to stay real. That was the map that I was considering initially, okay? So what we did was that we write this evolution, something like a Rodriguez formula, and then by comparing with these quaternions, with the rotation metrics written in terms of quaternions I showed you, if I want to have a non-trivial Hopf map, I have to map the time evolution to a column or a combination of column or a row of the rotation metrics. Those are the things that defines the Hopf map. So that's how I identify the quaternion components as this part, and then this is the imaginary components of the quaternions. And then by restricting myself, just like, oh, I want to have a Hopf map, we write down some matrix, 3 by 3 matrices that maps this time evolving state back to an S2. So when you sandwich the time evolving state with these matrices, it becomes real again. So I define a two sphere. And that is the thing that gives me a Hopf map. Okay, so this is something like an effective log sphere in terms of sigma x, y, z. I have some three-dimensional space that maps, that helps me to see this Hopf map. So how does it work? So if this Hamiltonian has some non-trivial Euler number, I can also express this thing by using the third eigenstate. And then this third eigenstate, as I showed you, it must be wrapping the block sphere. Okay, so it has this purple field everywhere, completely wrapping. And then imagine that I start with some state that points the same direction all the time. When I quench it, this state is going to start evolving around this vector. Okay, so if this is the x-axis, and then if I am in the positive x hemisphere, so this rotation is counterclockwise. Okay, and then if I am on the other side of the sphere, it's going to rotate anticlockwise. So two sides of the sphere is going to rotate differently. And then more interestingly, this evolution itself, so this can be identified as a pi rotation of the Hamiltonian. So that's what I encrypted here as pi. But without, so how I can identify this thing as pi rotation is that, so this is something actually not conventional, because, so, for that term of the, so normally I have sine theta half, some h, sigma, some psi here, right? Or for that evolution. So a pi rotation is going to give me no unit here. And then this Hamiltonian, if you actually write down in terms of the elements of these third eigenstate, you will see that this really effect of this thing is really just a pi rotation, if you just like compare it. So that's why it just like covers the sphere and uncovers it on the other part. So this allows me to write a map between the Hopf map, the Euler number dictated by this in, and then when I have the Hopf map, I have the linking number. So how does this look like experimentally? This looks like that by using this new effective block sphere that I could cook up. So what I do is that I start with some completely trivial state, and I suddenly quench with a Euler Hamiltonian that has non-trivial Euler structure in it, encoded in it. And then this state is evolving. I'm just like doing my time evolution normally, okay? And whenever it just like, I decide 2 points. Here, I decided the plus x and minus x on this effective block sphere. So whenever the state is pointing along plus x, I put a blue dot here. And for the minus x, I put a purple dot there. And then I just like trace them along the time evolution. And then you see that they link twice in the Brilliant zone. And following this monopole, anti-monopole structure that this orientable Euler class has, for the positive hemisphere that lies with my initial state, it links. And then for the other side, until linked is not a word, but links with the opposite sign, okay? So, and these monopole and anti-monopole they live in different parts of the momentum space. So they are completely stable, okay? So they cannot annihilate each other. And this, so if I have Euler class 2, I have these 2 linkings with opposite sign. And if I have Euler class 4, they link 4 times. And this is how it looks like from the top. And we also predicted some Hopf tori that instead of taking the inverse image of 1 point on the block sphere, if you take the inverse image of a circle, inverse image of a circle is a 2 torus in your original parameter space, which means that if you have a torus, this is non-trivial. And then for Euler, we have 2 toruses in different parts of the state. And then these, in the Chern case, these are actually already measurable. For the Chern, I showed you the linking, and then torus has been also measured in China. But this proposal has been picked up by trapped ion experiments, actually, and they quench with a non-trivial Euler Hamiltonian, and then they really detect this monopole, anti-monopole, skyrmion, anti-skyrmion structure in the vector field. And then when Euler class is non-trivial here, you can have, by the way, you can have additional images. You just need to count whether they link, how many times they are linking. And then here they see this linking and with the opposite signs actually very clearly, that I find always fascinating. And if the Euler class is trivial in the Hamiltonian, there is no linking. So nice. So, and one point is that, so this image is so clear, and then even if for our churn number experiment actually, so it wasn't, I mean, it is clear, but this is remarkably clear. The reason is that, so here, this was done in a Haldane model, and then Hamburg was engineering this thing in the real space. Okay, so your Hamiltonian has non-trivial topology, but you're engineering in the real space, and then, oh yes, I mean, things are dirty, experimentally measurable. It's amazing that like you can get a clear signal out of it. But here they engineered it directly in the momentum space with the trapped ions. And if you engineer directly the momentum space Hamiltonian, things can become actually not clear. So with that, in my remaining time, I want to quickly tell you about this anomalous Floquet invariance. Because when I have a two-dimensional system, and then when I consider periodic driving is periodic, right? So I'm already in a 2+1 dimensional space. And then if my Hamiltonian lives in a two-dimensional Hilbert space, I mean, this awfully looks like a Hopf map. And I actually express the Floquet invariance in terms of these linking numbers. And the answer to that is yes. So this is the winding number. It is an integral on dt and d squared t in this three-dimensional parameter space. So, but now, and then as a parameter, so these kx, ky, t already forms a two torus. So now I consider some two-band Hamiltonian as a minimal model because this is a single gap topology. I want some Chern class. And Hopf invariant can be written in terms of either the quaternion components or as a Chern-Simons form, which is written as the one-form connection wedge two-form curvature. And then we showed that in this paper, I don't want to go into too much details, but we show in this paper that like this winding number for the time unitaries can be actually with some, it turned out to be, initially gave us some headache, but then when the math works, eventually it looks so nice and clean that you wonder why you had that much trouble doing it. But this can be directly expressed. This winding number can be analytically proven to be equal to the Hopf number. This has been quite useful in several different settings. But one trick in Floquet, what's happening is that, I mean, we know that Hamiltonian is periodic, okay? But Hamiltonian is not the thing that you are actually interested in the Floquet. I mean, you are interested in, but it is the time evolution operator that governs. And then you're getting the spectrum of the time evolution operator. And then this time evolution operator can be written as a product of a micromotion and then some effective Hamiltonian. So when you calculate this thing for the entire period, these bands are just the eigenstates of the effective Hamiltonian. This time evolution operator is not periodic, right? In generally, I just like have some states, I just like apply some drive. It doesn't have to come back to itself at the end of one period. What comes back to itself at the end of one period is the micromotion operator. So that is why we need to isolate it. And that's why in the original, Radner paper and also Kitagawa, they had to apply this inverse map to get rid of this part. So micromotion forms this three torus. And then you can find this micromotion in two different ways. So imagine, what I can trace, the thing that I'm observing is the left-hand side, right? But I want to access this one because this is the guy that's periodic at the end of one period. So what I can do is that I can multiply this thing with e to power plus I HFT, okay? But this Floquet Hamiltonian can be found in two different ways. I need to calculate some branch cut. I need to put a branch cut to do this thing because this forms a circle time evolution. I can either put my branch cut there and then calculate one Floquet Hamiltonian like that, or I can put a branch cut there and then calculate the Floquet Hamiltonian like that. So I can apply this thing in two different ways and then write the micromotion for these two different branch cuts. And that's what we need to do. So there are actually two Hopf maps. And when I have this time, when I isolated the time evolution operator, if the bands are flat, so if this time evolution operator is identity, when this is periodic, it means that e to power I 0, and then so my quasi-energy bands must be degenerate, and then they can be degenerate. So I have this thing, but I can make them degenerate like this, or I can push them back into Floquet Boolean zone edges and make them degenerate like that, then measuring the winding in that case. So this is what we did. And then starting from a completely trivial state, we quench with a non-trivial Euler Hamiltonian to validate this analytical formula that we actually also drive. So then we checked how the evolution is happening on the Bloch sphere, and then we take inverse images of south and north poles. So this has been done for this phase. So there is no winding number in zero gap, but winding number in pi gap is 1. And then when we concentrate on the zero gap, these inverse images, they don't link. They look something like this in my 3 torus. And then if I look at the winding number in the pi gap, they link something like this. Okay, so it tells you that like winding number can be expressed as linking number. So with this, let me conclude. So including also yesterday, so starting with an introduction on topology and then how this simple Chern number looks like, and then in a geometric way. And then this geometric way can be even extended to larger Hilbert spaces S2 to SUN. So, and this can be actually quite powerful, giving this z-axis character to all gamma matrices. But then when I include, in general, when I go to out of equilibrium settings, like blockade driving, or by doing quenches, adiabatic pumps. I mean, there are a lot of directions that you can go under out of equilibrium settings that I haven't covered. So things you can just like discover new physics there, new topological invariants, which was my focus for these talks. And in the case of Floquet topology, for example, we can have anomalous Floquet topology that things are happening in the anomalous gap. And then this can be again measured experimentally with intriguing signatures. But then with this other more, things with this newly emerging topology with intriguing properties that they have non-abelian braiding in the band singularities that you just need to make them move around, and then even temperature can do this thing actually. And then they have been also predicted in phonon modes. What you need is just C2T symmetry. If your Hamiltonian has a real form, you can braid them and induce after inducing band topology. But if we combine this Euler class non-abelian braiding properties with the Floquet drive, there can be also nodes here, which we know that are experimentally relevant and observable. We can also braid with them, and then we can come to anomalous phases, anomalous non-abelian phases that can only exist out of equilibrium and through non-abelian braiding. And on top of it, we did quench signatures. They also give interesting quench signatures that have been also experimentally observed. So with this, thank you for listening yesterday and today. If you have any questions, I'm happy to. Okay. Yeah, so when I have this, so what we did here is that, and what I mean with more robust is that, so I mean, you can have impurities and then edge states go around them. So that's robustness, but that's why I put these things in quotation marks. So what I mean is that here we were considering the wave packet dynamics. So when I have Floquet, so I can have 2 bands. So I can have some edge states here, which is something that I can get in the equilibrium. So I can have bands there, I can have edge states there, which is equivalent to a Chern class in some way. And then I can have this anomalous thing, what I can do. So what we considered is that like we just like took a edge system. So and then we introduced wave packets. We introduced wave packets at the edge, and then we just like observing how they disperse at the edge. So so this is the edge sites, and then this is time, the thing that I introduced, how it's evolving along. So it has to follow a chiral edge dynamic. So that's something we know. But what we were trying to do is actually that, is there anything different between these two? Because this is something, I mean, this has, to begin with, this has Chern number 0, although it has edge states. So this is the dynamics in the anomalous phase, and this is the dynamics in the Hall-Lane phases. But when I have the edge states in these ones, and then these things here, the depending on how your edge states overlap with your bulk states, some probability is going to disperse. That's something we know. But what was surprising was that anomalous Floquet phases and then anomalous edge states actually are much easier to populate. And then the wave packet you put disperses into bulk much less. And this is visible in the color scale here, although not that visible in the scale, but we can actually quantify this thing. So here we just like induce the wave packet at the same place across different points in different phases here, like this is for this cut along the line. So we induce the wave packet, and then we look at what is the probability overlap of this wave packet with the edge states that are present. In this case, there are two edge states. So if for this one, so they actually occur at different momenta. This one occurs at gamma points, this one occurs at K. So they are well separate. Any wave packet you put goes and prefers this one. To populate this one, you need to apply a kick. That's all good. I can populate individual gaps. But here, with this one, I'm actually P0, so I'm applying a kick here to calculate, to compare with this 1-0 gap. So I'm comparing this state with this one. They both occur at K point. So I apply the same kick targeting the thing that they want, but more probability is end up in the 0 gap states, 0 gap edge states. There is also some remnant probability in the pi gap states. Some of the probability goes there, but there is a clear signature that goes there. And then this dashed lines is the total probability that goes there. And then same thing happens when you also compare these other Haldane-like phases. So now the edge states are in pi gap, and then they occur at gamma points. So I don't apply any kick. I just put the wave packet. They just like evolve. And then, but in this case, it's much easier that like more probability goes to edge states. And this is the way that I think about this thing is that when I have a finite size system, so I mean the ratio of edge states and bulk states are fixed. I mean you can just like count how many edge states. That's when you have more states, when you have larger system sizes. So edge and bulk separates more. If you look at the eigenstates, they just like if you have a smaller system, edge states go deeper into the thing more. But what's happening is that, so in terms of the system sizes, I consider two same systems, right? But here, this system in the 1-1 phase, more state must be localized at the thing. So I mean, eigenstates, so imagine that I have 100 sites in my system. Some of them are on the edge, some of them are in the bulk. Here, this 100, I must have 100 eigenstates, but more of them must be of the edge character. So that's why edge and bulk separates more in the anomalous phase. And then in terms of edge transport and dynamics, they give much clearer signature in these dynamics. And this has been also in Munich experimentally, it's easier. If you have anomalous edge system, it's easier to, is that, yeah.
So I'm not sure if I followed like everything, you know, like from today's talk, but if I understood correctly, there are like different classes of topology, and then there are the Chern classes, and there are also these Euler or
Yes.
higher band classes.
Yes.
Now, if you take just a band system and you shake it periodically, but resonantly, then you know that you're going to open up absorption gaps, which is going to increase the number of bands. So my question is, can I start with a boring or a Chern system, shake it resonantly, and then change the topology to Euler or some other?
Oh. You mean with some Floquet replicas that evolving? No, because so you want to start with some 2-band system.
I could start with a single band system, but for as long as, you know,
Yes.
I can create, you know, the topology with
Yes.
the drive, right? So the drive basically increases the number of bands.
Yeah, not really. I don't know whether that falls into that's not exactly free lunch, but I don't know, it's in terms of just like not extending your Hilbert space. I tried something similar to it, and then it doesn't work. Why? Because so to have this Euler topology, you really need to have the dry band. Okay? So when you have the same bands talking with itself, or just like opening with its replicas, you don't form the dry band. It's in a way, it's the same thing. And then so that's why like you really need to start with minimum 3 bands to realize the Euler. You can bring more things, but in a way, because these are the replicas of the same band, right? So, and then these inversions, the way that like I just like have the dry band and I'm rotating it around doesn't work. So you really, your Hilbert space must have this structure, and then you do something interesting with it. So that, yeah, you really minimal, you can bring more things. You can have 4 bands. The rule of the game is that you always braid with the adjacent gaps. You can have different, like for 4 bands, you can have 2 different subsets. This one has some Euler, this one has some Euler. So, but yeah, you need to start with them.
Okay, thanks.
Sorry, maybe just following up on that question, I was thinking that, so we heard this talks about quasi-periodic driving, where essentially you have multiple frequencies which can act as multiple dimensions. So can that actually enable the realization of some of these Euler classes and such, starting from a more trivial situation?
So, yeah. So in terms of, yes, in principle, Euler class, you can actually see it in several different settings. So this can be also seen in non-Hermitian exceptional points, you know. All you need is that, all you need really is that like 3 bands, and then you should be able to cast the Hamiltonian in a real form. So you need to have C to T or PT symmetry. And then as long as that, this can be seen. And then, so because we want to do the braiding, exactly, so we need minimum 2-dimensional parameter space. That's what we want to be, but you can also have 3-dimensional stuff. In terms of extending the Hilbert spaces, so as long as you have, exactly, so for the quasi-periodic driving right now, I think it would work. Yes. Yeah, but yeah, I need to think about it. Yeah.
Any more questions? If not, then let's thank Noor again and give her coffee.